Okay, sir.
Yeah.
Okay. Tomorrow you will take class, sir, and
Yeah, I
weekend
will
only.
take as usual. Do you have classes, right, or not? As
Yes, sir.
from
Yes, sir. We have classes, sir.
yeah, yeah, as usual from tomorrow.
Okay, sir. Thank you, sir.
Class times. Okay. Did you try this exercise? This producing two rectangles. Am I audible first?
Yes, sir. You are
Yeah,
audible, sir.
fine, fine. Yeah.
Sir, I didn't try this one, sir. I
Yeah,
tried to solve previous exercises, sir.
okay, fine. Uh, like you think of it right now, like 2 minutes. It don't take much time. As I will repeat one more time, it is quite essential to approximating functions. Literally, how neural networks are doing internally to bring out a particular to bring out a function approximation. That's what we have seen at very first, like theoretically, like a function from the what we say sigma net or sigma pi net, whatever. That is an approximator function. Like the series of functions, it converges to a function at the limiting state. That's what we have seen. But actually, um, the function, if you remember, like if you think of like f of x is a representation of summation of the weights, some beta i's, uh, g of a fine function of x's. This is what in general we can say. We can write up a function from the sigma nets, right? Over I, from over I, like I is representing over the neurons. So this is actually the same whatever we have written here. Now we are saying that any function f of x, so no matter whatever function f of x give me, I can closely go through closely go to a any given target function. That's what we have seen theoretically. Now the thing is, you should clearly look at how that is going to how that is approximating. How are we approximating that one with a simple examples? Unless otherwise, like you feel like it is, you never see really how f of x is coming out of this one. How it is actually looking through a f of x. Suppose this piece is a function, or this piece is a function or a target function. Now we are trying to find out a close approximation using these rules. So for that, we have started with without any g. I could say here g is not. I do not say that without any g. G is a simple uh, identity, or you can say that g is a signal, or simply activation function of a step function which takes 0 for the x less than 0, or 1 if x greater than 1. Even you can say that you are producing the signal, uh, you are producing the signal only. This is a affine function. Let me write up. Let's say if our f of x is just simply x minus b. Here the weight is 1, and usually the affine function a of x for R to R. I'm not talking about any higher dimensions right now. W x or ax plus b. You can say that these are the weights. Only two weights are there, affine function and the real line, a single input or R to R. So now if I choose a equal to 1 and b is leave it as it is, and let me keep it as a b as a minus 1. So this is a simple x minus b. That is my affine function fixed rate. Then if the computational unit, if we design with x as a input and b as a bias, then it would be there b as minus 1 and x as no, not b as minus 1. uh, b is same thing, but I keep minus b instead of b. um, doesn't matter as we go ahead with the biases, positives or negatives, there is no irrespective of it. So you don't need to worry about that one. I can keep it as this one. The weight w here I am keeping it as a 1. So now what will come here when we summing it up, that is x plus b will come up single, there is nothing else summation. Now this x plus b, usually we apply an activation function g. What activation function is it is simply a kind of a continuous function. We generally talk about it, but here I don't need to call this as a continuous function. I take it as some kind of threshold, let's say, or maybe I will keep it in other of x plus b. The threshold is a kind of uh, the 0 in this case, I can say, or maybe another logic function. I can say that if x if x is um, if x is greater than b, I can say. So we are receiving input x and receiving a b, and only the two things are coming, x and b. And from that I am making a, usually we make a x plus b. Instead of that one, I will keep it as like to get a signal. My point is to achieve a signal. The this one signal of kind of like this one, this signal at B. That means that uh, this below B, below B it produces 0, above B it produces 1. For that, what do we do? Like if then if we can write x less than b, it is 0, 1. If x greater than b, so this we can, and that means like you have two things in front of you, x and b, and the threshold function it is doing like our target is to produce a positive signal. That means like if x greater than b, if x greater than b, or you can write up like if x minus b greater than 0, that you can express this one also same thing, x minus b greater than 0, then we produce a 1, otherwise it won't produce anything. So literally finally we are getting the binary neurons as we have seen that earlier, like binary neurons 0 comma 1, 0 comma 1, the outputs like either true or false, or true true false false, all those things. So you will get again here a binary neuron, either signal is either 0 or 1 only. The answers are either 0 comma 1. If it is 0, then that means that the signal is uh, the flat at 0, and if it is above x, if x is above b, then we are producing a 1. So there is a peak here. This peak is the thing which is jumping the signal, it is causing a signal. That is how we are taking the advantage of uh, the binary. So finally we are expecting a binary only, there is nothing else. We are not producing any kind of a function relationship, just using simple binary function 0 comma 1 from the real. That means like you are producing f is a function from r to 0 comma 1. Simply, no matter whatever x you provide, you will get always you will get a signal with below b it is 0 and above b it is 1. Now combinations of these signals, several combinations, that's what we have seen yesterday. Like you have a couple of signals, like if you take two signals, one is at b1 and other one is at b2. You have two signals now. With these two signals, you can manipulate them to bring out a rectangle. This one, like that's what a rectangle shaped signal, a box shaped, I could say. This signal. That is what we have in functional manipulation. That is f1 minus f2. That is linear combination of the signals. That is, you can see in the neural network, we are supplying an x with weight 1, and that is signal. This is the x minus b. It is actually doing what it is doing. The signal is jumping. This is the function. I kept it as something like this one. This is nothing but the one which I have just explained. This one. This is taking the signal at, it is activating. That means you can say why the activation means we are keeping all the time flat 0 unless x reaches the BIOS. So the BIOS is the key. It is allowing the neuron to activate until it reaches the B. Once the neuron, the X value reaches B, immediately this neuron gets activated and it is producing a pulse. That is signal 1 we can see. And if we have couple of such signals, couple of such functions with different biases b1 b2 numbers, then we can produce multiple such sharp signals. So that is why this symbol is actually representing the this function as a, you can say, some engineering terminology uses here, mathematical, I don't know whether it comes in heavy side functions. Do you use this one? as a heaviside function.
Yes, sir. In I guess it difference complex analysis last semester, sir.
Okay, yeah. Usually, sometimes you call it as a heaviside functions. Okay, whatever the function name it is. Um, so that makes sense. Like it is a two-state function. So this neuron is actually doing whether it is activated through bias or not. If it is activated at the bias, then it is produces a pulse, and it is not, then it is still zero. It is do not contribute anything. Such combinations, such several combinations, we can see different things. That's what the F1 is activated at B1, F2 is activated at B2, and combination of F1 and F2, linear combination of F1 and F2 with same weights, with the reciprocal, with the negation of the cell. We can see a box, this one. Now, with this, now if I wanted to produce this one, now think of it, 2 minutes, all of you, to produce what kind of combination or how many such signals are required to produce this structure.
Sir, I have sent one picture, sir. Could you check that one, sir, in chat? Is this correct or not for this one, sir?
Okay. Okay, let's draw whatever you should give me. Okay, this is x, and x minus b1, x minus b2, x minus b3. So finally you are having w1 minus w1 minus w2.
So not like this one, sir. We take two outputs, sir. W1 minus W1.
Okay,
Then
okay. No, this is, I don't suggest, like we are
after,
allowing single layer neurons.
okay, only single layer neuron.
Single layer, single hidden layer. I'm not talking about multi hidden layer, multi layer neural networks. Single hidden layers.
So, for multi-layer, that one is correct or wrong, sir?
That we will see. Multi layers may be possible. I'm not verifying that right now, but I
Okay,
just
sir.
want with a single hidden layer.
Okay, sir.
Single hidden layer structures. Yeah, now with the single hidden layer structure, how many neurons are required to produce this one? Once you produce this signal, then you are very comfortable to approximate functions.
Sir, for single layer, I am not sure that, but I think it will be three hidden neurons, sir.
Still three hidden neurons, then okay, let's construct it.
Yes,
How?
sir. W1 and second, this one is W2 minus W1 and last one is minus W2. If we take,
This one is minus W2.
yes, sir. And above is this one is W2 minus W1, sir.
W2 minus W1.
Yes, sir.
Okay.
Maybe.
Okay, let's see. First one is producing. Let's draw all the three pieces first. Then let me keep a plot here. Let me keep it as a B1 here, B2 here, and B3 here. Hmm. We take that. So first one is activated as soon as it achieves the B1, that is the first signal is a kind of comes, activates here. This is the first signal, and the second signal is activates this one. uh, at B2 you are maintaining the same height or it is a different height?
Sir, for B2 we multiply W2 minus W1, sir.
Okay, that means it is a different weight.
Yes, sir.
This is a different weight, and B3 is again different weight. So which one is larger? So B3,
W W2 is larger, sir. W2.
W2 is larger.
Yes, sir. Greater than W1, sir. Right.
So if now the thing is, if W1 is positive, W2 is also positive. Okay, W1 is positive, W2 is positive, then minus W2 is negative, right? If we consider
Yes, sir.
W1 is positive, both W1 and W2 are positives, then minus W2 is negative. Then last signal, let me draw first the X minus B3. If I draw according to you, then minus W3 puts the signal down somewhere. And this puts the signal down, right? Because of minus.
Yes, sir.
So now the question is about whether W2 minus W1 is positive or negative.
So it is positive because W2 is greater than W1.
So okay, if you maintain this 2 with the relation W2 is greater than W1, these three are assumed, both are positive and W2 is greater than W1, and you are keeping minus W2 and B3, then this height is W3, this height is W1, and then uh, if you keep maintain,
This height is W2 also, sir. B3 W2.
okay, okay, this is the W2, yeah, right, right, yeah, W2. Hmm. Then what is the resultant signal after summing up all these three? No, this one we need to produce at B2. W1 and W2 are like this. Now at B2, how it looks like? Let me, and as you mentioned, W2 is larger, so I will keep this W2 is a little bit below, so that indicates that it is much larger. And this one is W1 is smaller than that. Yeah. Now combining these two, what will come up? At B till B1 to B2, W1 maintains the same thing, right? This signal. From B2 to B3, what is going to be happening? Again, still it is same thing. The resultant signal, I am keeping it in the green color. This is still B1, and this is a W1 is keep maintaining till W3. If you no matter whatever you sum it up, because this is a zero with this W1 is a zero, W1 only, right? This is the resultant green signal. Now what you are doing operation W Oh, there is another signal is there. Okay, I forget that. Okay. Uh, yeah, let me draw that signal to three signals, not two signals. Okay. So what is the third signal at B2? What you are maintaining at B2 is still come here. That's you are keeping it as a W2 minus W1. So is W2 minus
Yes,
W1 positive?
yes, sir. Positive less than, but less than W1, sir.
Less than W1. That means like you are keeping, of course, W2 minus W1 is greater than 0. But how do we say that it is less than W1? We cannot
Uh,
say.
yes, sir. We can't. Yes, sir. We can't, sir. Maybe it's greater than also, sir.
Yeah, it can be go up as well.
Yes, sir.
You can't say that. Yeah.
And if we assume go up, sir, then maybe if then maybe our if we add more condition like W2 minus W1 also greater than W1,
Yeah. So
then
then okay, let's see if this one is the thing. So the height would be kind of like this one because of no, this won't come here actually as WT is positive, WT is down, and W1 is this one, and um, and actually W2 is a negative side domination, W1 is positive side domination. The both if we combine, finally what would come up? The signal comes down.
no, sir, because we consider W1 and W2 both are positive and W2 is
W1
greater
W2
than
are both are positive, but W2 is a negation. This is a negative side as
for
this
B.
minus W2.
That one is correct, sir. But for second signal, sir, that
Yeah,
one.
second signal is W2 minus W1, and W2 minus W1. Okay, so W2 is positive, W1 is also positive. Okay, W1 is also positive. Okay, I can take our things like, okay, let me keep it as this one. This is the signal. This is a resultant of W2 minus W1,
Yes, sir.
right? This is minus W2, I could say. Then there is no confusion. So now summing all these three signals, what is the resultant one? This V1 till 0, and
Yes, sir.
this do not have anything.
And this will come only W2, sir. After B2 to B3 comes only W2. If
This
we add
B2 to B3 only
till W2, sir.
till this would be W2 minus W1 height, right?
W2, if we sum up, then W2 minus W1 plus W1 also, na, sir.
And
Then
this one is there, W1, so that uh, it will be
it will
come
be,
down.
yes, sir. It will come only W2
It will come to W2. Okay,
or not come down. It may up, sir, because
may it go
we,
up? Yeah, exactly.
yes, sir.
May it go up. Yeah, this would be up to till this one.
Yes, sir.
Then
And then again we sum up W2
W2.
W2 minus W1, and then this is minus W2. Then it will come minus W1, sir.
Here three now after B3 there are three things.
So then it will sum up, sir.
This
Oh,
one, this one, this one need to sum up.
this, yes, sir. So then
All the three
it will
things.
become zero, sir.
Oh, okay. Oh,
Because W2 minus W1, this
now
one,
let me see.
uh,
This one it is a W2 minus W1. This is a W1. It is a minus W2.
yes, sir.
Okay. So this is coming 0.
Yes, sir.
Yeah. Okay. Do we have now my question is about is do we have flexibility to produce with these three neurons? Um, yeah, of course, this is correct, presumably because of one reason that like there is a joint connection here that's allowing to make the things done. So if if you wanted to produce two signals independently, like this one with this one, and like this one, I think it is not possible with three.
Sir, yes, sir. This is not possible if we do like this one, sir.
Yeah.
Mm.
So
We add
this
more neurons,
we
like
need to adjust because of this junction is allowing to reduce a one linear inequation equation so that jointly is acting it as. So if you write down all the inequations or equations, two equations will come up same because of B2, and both the signals are maintaining the same at one junction. Okay, now um, with this construction, or you maintain a separate construction for independent signals for the boxes. These weights keep this one as the axis, and you have biases like this, and finally you will receive either 0 or 1. That is finally what we are getting, only either 0 or 1 with the not 0 or 1 especially, but the 0 or 1s are multiplied with these weights and they produce in the linear combination of those weights, the linear combination of uh, the weights sitting on them with binary, this one, the summation of all these things, so that you will be achieving some kind of signal production. Now now you take a any function like this, any function like this, any piece of function like in the from the part of the x square or part of the x cube or sin x or tan x, no matter whatever function. Now if you wanted to keep this one with the several such pieces, several such one, this one, then you are filling all those signals. Like let's say if I say that fill this region A to B, let's say instead of a you can take up A equal to 1 to B equal to 3, just in the within these 2 units of distance you fill 1000 such rectangles. Then they must be tiny, there must be tiny signals with producing all these, the combinations of all those uh, neural networks will give a close approximation to f of x with the simple this one. All these are rectangles, the signals are like this one only, all the linear combinations of side by side ones, and these things you go with all possible no matter, you divide the entire region and approximate with all those signals, then you are literally your neural network f of x with right choice of b ones, right choice of w ones, and they represent the function. So now you should know that very clearly the controls, there are two controls here. First control is the width control. Width is controlled by the biases. Biases control the widths. That is what like you are always the width of this one. If you think of this one like the width is the B1 and B2. In the first two neurons, if you take up the b2 minus b1 is this width, and the height is the amplitude of the signal, that is the weight you are multiplying at the outcome. This is defined by the height. So the outcome weights, the output weights are deciding the height. Now if I wanted to approximate, excuse me, if I wanted to approximate f of x, that is any piece of continuous function, then with 1000 such rectangles with suitable biases, so from here to here, so you need to choose several. We are not choosing biases actually. You don't. These are the controls. The biases are representing the rectangles, and the widths, the weights. What actually the weights are the controls of the heights. Now here in this case, to write up here, we manually choose some kind of signals b1 b2, we fixed them up, but now these b1 b2 or w1 w2s are need to be choose for 1000 such rectangles. How they are driven, we are not picking up manually, and how do we pick up them? So now that is the point of learning procedure. In the learning, you apply this f of x. You are targeting all the time. The signal should be mentioned like for given this x, you should take some samples in between a and b. The samples, let's say, um, let's say like 1000 samples you take up, 1000 points you take up. For every point you take up, uh, for that you have a f of x value already, the x you know it, and the function, actual function you know it. For this x, that there is an f of x, you apply a supervised learning whether this signal is meeting meeting this f of x or not. That means that for a particular point you are producing a signal, that signal you are always correcting with these weights in terms of supervised learning. So now generally first initially you don't have any all such signals. So if you decide 1000 and keep 1000 such neurons with B1, B2, B3 and so on, B1000 without having any, fixed things, they are random. And then these W's also are random. Now you supply the function f of x and f of x and train the neural network with the functional values. So I allow the neural network to adjust on its own these biases and weights. So finally, ultimately, because of the nature of this condition on the neural network and on each neuron, that is a signal neurons only, definitely there is no way any linear combination with this neural structure. It is a boxed matrix only, boxed structure only. Whether it is no matter whatever random you choose, it will come the structures like this. Whether it is maybe it go up down like this, definitely it will come a signal. Now your target training procedure is to adjust the signals, adjust the weights, that is amplitude of each signal and width of each signal, such that they come perfectly fit under the hood of this f of x perfectly, the heights. That will be the training procedure. Training will allow you to adjust these widths and biases so that they align all the things uh, into a proper way. Now this f of x, the approximated f of x, is literally a boxed approximation. It's a signal approximation completely. The our continuous function is your continuous function, whatever continuous function, sin x or cos x, x square, no matter any continuous function, that is now literally it is approximated by a piecewise continuous boxes. Now, now you don't think this as a boxes, like this is actually signal of a single one. Like it is something like it goes here and comes down. And it won't comes down, like it goes here like this. I just given for the feeling of, like, the boxes, but literally it is at the end signal. It is something like this only. So this is in between these two, so that it is just a two signal like this. If it is multiple, then it would be something like this one or this one. Let me draw something. Till the end point, it will be like this. Till the beginning, it somewhere goes here. This one then comes down. So no matter, until the end, it will maintain the same boxed signal till end of the signal. If it is out of the range, then it will come to zero again. The signals are zeros at this point. So now this is a piecewise continuous function. Piecewise continuous function. So these are all like discontinuous at these points, as by nature of it is produced by signal. Okay, that is what, like, function approximation. Actually, we are approximating just like the Riemann integration. How do we the Riemann integration? We are simply approximated the boxes to find out the area under the curve. That's what we have used it to talk. Now using this, after approximating f of x, any function, you can find out Riemann integration too. You will get a Riemann sum f of x. Now you have all the signals. Every signal acts as a rectangle. Every signal, the peak acts as a rectangle. Now if you take the area of each rectangle, then that will be the area under the curve. So your neural network has everything now. If you, after training, your f of x is a close representation of original function. Now using this neural network f of x is in the kind of like summation. If you take I equal to 1 to m neurons with you have specific weights with the signal, in this case, instead of g, signal of affine functions, that is ai of x, this one. So this is a close approximator of f of x with the boxed nature. Okay, now you can draw this one. Once you have this f of x with you, you can see how you can draw the function. This m is actually the number of boxes, how many such neurons you can keep it, so that they are adjacent to side by side, so that it is representing that one, as we have seen just for this case. Now, now how can I go ahead with the same thing with the smooth function, not a piecewise continuous. I need a continuous function, so that I need to allow this activation function to behave a continuous function rather than a signal. Okay, so now let us see the activation function. No, I will take up some kind of take signal, what the same. I will continue with that. Suppose okay, let me take up at 0 in general, not at the bias. So this is signal definition. Below 0 it is 0, above 0 it is 1. So because of this nature, this jump of several such signal combinations, we are getting this piecewise continuous function, which is approximating our function. That is what we have discussed. Now, if I allow this piecewise with a little bit a smooth, let me take up a kind of like, if I allow this some kind of smoothness, this is, no, not this is also smoothness. And then what will happen to my nature of approximation? Anything of? If I allow slightly, if I brought it down this peak, a straight peak into a curve nature, still can I approximate? So how it is, how it, what will be the effect in this?
So after certain times, sir, there is no spikes in our signal, sir. It will
Yeah,
become
there won't be
continu.
any sharp signal definitely, but
Yes, yes,
what will happen at those signal? This the jumps should become the curves. They
yes,
smoothen. They are
yes,
we
yes,
are we are not like steps,
yes,
the
yes,
sharp steps. We are smoothing them. Like we are kind of like the approximator, whatever we use it. The that is also again depends upon how much smoothness you want it to be. Like you even if you go with a like you have a lot of choices. Say smooths. How much smoothness allow you allow it, like if you take up a blatant smoothness or heavy smoothness, so there are a lot of choices of smoothness you can allowed here. Otherwise you can go close to this one but very less smoothness like one such this one. You are just only maintaining a, you are just simply allowed this peak into a small variation so that it is coming up like a slow very tiny smoothness. So there are variations of the smoothness. So how do we write up that equation? If that is can be written as all the possible smoothness, that is what sigmoid of x talks about. That is 1 by 1 plus e power minus x is the signal which is actually the median signal, that is that goes middle of these two signals. See, if you notice, everything is passing different points based on how much smoothness it is producing. Now, if we think of this one, some kind of signal, and if I keep some kind of parameter here, alpha x, that alpha is the one which is varying the signal, this alpha x. So if you keep um, uh, so if you keep alpha, uh, which one is produces the when what value for at what value of alpha it is the signal, it's a peak signal like heaviside function, whether it is a small alpha or large alpha or what. I mean how it is varying, how it is close to say, if I wanted to produce which is very much close to the peak function, very much close to peak function, but that is not the peak function, then what alpha I should keep it. Okay, you and try this one in the Desmos and feel it. Okay, write this one in the Desmos.
Okay, sir.
I urge you to do something like write up these things in the Desmos all the time. Like, okay, I will share. Otherwise, if you are not knowing how to use the Desmos or properly, I will share some Desmos things so that you can see the feel of or power of Desmos. You can. So could you able to see my screen, which is I'm presenting right now, Desmos?
Yes, sir.
Yeah, fine. Uh, so if you take this one, like, if you wanted to write up your function f of x equal to 1 divided by 1 plus e is minus x. So you can see that, like, now if I keep it something called a, I just need to just keep it a slider here. Now you can think of as I move a, how it is behaving the sigmoid function. Okay? So this is the signal. If I change my a to the negative side, it is getting reverse. The signal is getting reverse. And if I keep my a is the positive side, it is at a equal to 1, it is what we call it as a sigmoid. That is this one. Like, it's a at maximum allowed gradient, I mean the smoothness. Then as I am moving towards positive, the gradient is increasing. It is it is the this is the point where the you call it as a inflation. That is actually the signal. The slope at that point is rising. As you tend to infinity, it will go and close to, um, like, let me increase a to 100, from, let's say, minus 10. Yeah. Now if I keep increasing this a, and you can see that it is close to Heaviside function. As a tends to infinity, this becomes an Heaviside function. That's signal, whatever I would say. So we don't you can control the signal of the approximation at each peak, how much variation you want it to be allowed. Like, you can control this a, the parameter, uh, so that you can get approximation into what kind of approximation you are thinking of in our function approximation. This is a one kind of, like, allowing the smoothness into the sigmoid, mm, a sigmoid function, activation function. So now the same exercise, uh, if you repeat with if you repeat with any function approximation, like if you take piece of any function, then I allow sigma of x instead of signal, then your rectangles become the smooth rectangles, that is the smooth curves, and they will try to now approximate the curve, and it is much better than the sharp signal. Sharp signals is actually, it is they, the top notch, whatever horizontal line, it don't sit under a curve. They just close to it, but they behave, they are very close, but they don't sit along with the curve direction. But these things, this sigmoid allows to sit under the hood of the curve properly. And we cannot say that 100%, like again there is an error, always it is an approximation, but it will reduce definitely the error. Now your exercise or task, take a simple piece of example, like a part of, I'm not giving any function, you take up whatever a target function you choose of your own choice, and develop a neural network in Python. Take uh, 10 neurons or 50 neurons or 100 neurons, that's up to you, your choice, and maintain the one problem with the rectangles, one problem with the sigmoid on the same size of same architecture neural network, and look at it how close approximation they are, and which one is making the better sense in terms of um, error. So if you calculate the error difference between the norm difference between the original function and the approximated function for the both the cases, then you could see very clearly which one is outperforming the other. That is a kind of, like, the looking at how the approximation is going. Okay, so now you can feel that, like, I will tell you something, like I might have already drawn couple of such structures. I'm not sure. Yeah, there is some rectangles. Yeah, you can see here it is a one single piece of rectangle where single neuron, these biases are the ones which is, the biases are, you can see the how the width of a signal is changing in the red color, and the height is this one, the outside neuron, it's a single signal. Now you can implement a kind of, like, here it is a single neuron, this is only it is two neurons, h1 and h2, uh, both are jointly doing with the x minus b1 and with x minus b2. B1 is for this part and b2 is this one. B2 minus b1 is the width of this signal, and the height would be the amplitude which we are multiplying this one. So the height is, you can see the signal height is controlled in the neural network. So if you, like, it is simple, like x b1 we are passing, y1 is the first neuron, x computational, x minus b1, and y2 is x minus b2. The h1 is the function, the signal function. If it is y1 is less than b1, that is 0, y1 is greater than 0, that is 1, single signal. Similarly for the second neuron, if y2 is less than b2, it is 0, y2 is greater than b2, it is 1. Two such signals, and we are combining this h1 and h2 with this linear combination w1 with minus w1. So it is producing a resultant signal. Now my task is not this one. This is for to feel that one, but how we can think of this is happening in the higher dimension. That is what my intention of. Like, I'm coming out of the screen. Now you can implement multiple neurons, two more neurons, to produce a further signals here, like 2 3 4 signals, and update this one with, okay, maybe I will share this one with you right now so that you can think of share. So you can update this one with further neurons, and see that function approximation is happening with the simple signals. Okay. Now coming back to my original. Yeah, yeah. Now think something called the same thing. If I wanted to apply it for R2 to R, f is a function now. It is not from R to R. If it is R2 to R, so now your target function is something called surface. Let's say a surface of strip of kind like this. Now your domain is sitting here. Okay, your domain is now x and y. This is x, this is y. You have these things now. Now if I wanted to produce a signal, our aim is to approximate this strip over a domain, a particular rectangular domain that you can think of. I wanted to approximate this function. Let's say this is my f of x, f of x comma y. I don't say it is f of. So this is a surface. I just wanted to approximate that one. So for that, with again boxes, start with the boxes. Now here it is boxes is not just that one. Now the boxes must be what? It is a parallelepiped. I mean, these are cuboids. This one, a
Yes,
simple
sir.
cuboid, right? This one. Now think of it, how these cuboids can be produced using the same signal concept. What neural network? I need a single cuboid with the x and y. Like let me take the domain is like is sitting here, and this one I could say I could draw very perfectly. It is sitting inside a domain at some particular place here. I want a piece of domain, let's say in a particular region. I just wanted to keep the signal up, that is 1, and rest everywhere 0. Rest everywhere the function is settling to 0. That is the signal. The simple concept of in 1D, that is a kind of like signal. If it is less than 0, it is 0. It is this one, like 0 and 1. Now you can bring it this one to the somewhere origin or somewhere here. Here, and you can talk of this is a 1, rest everywhere it is 0. You can say that one too. I want this particular signal, a particular a cuboid construction, just like we have seen this simple construction. So this simple construction with with a proper height and proper width. Similarly, what could be can we can how do you what is the neural network? My question is, what is the neural uh, network architecture which produces this cuboid signal in R2. Okay, you try this one as an exercise and give me the neural network architecture which satisfies this one. So that once you know that if you can able to construct a single cuboid, then if you take any function f of x comma y, this is the function just instead of just simple f, and I can say this is f of x comma y. It is a two parameter function, two-dimensional function, so that you can keep such multiple cuboids. multiple cuboids under this domain, so that you are closely approximating the again f of x comma y. So now I think you are closely understanding actually what is geometrically happening under the neural network. Do you feel, do you sense that the approximation,
Yes, sir.
how activation function is actually doing the things? Am I, do you get it? At least I feel we
Yes,
cannot.
sir.
Yeah, the neural network is actually doing the same job we do it in mathematics, but here it is under a different setting, constructing pieces um, by supervised learning. But we know the function of x comma y, and we are constructing some kind of a sigma net. We are picking up some choice of sigma net and asking, allowing that sigma net function under adjusting the weights, so that the adjusting weights allowing to decide what kind of approximation single pieces are doing the job together. The neural network, single neuron is constructed, or few neurons jointly giving a kind of like approximation piece, and multiple such pieces are producing the required function of approximation. And now change in the activation functions, a change in the shape of this piece. Here, if you take simple signal kind of piece, and it is a kind of like this one, if you change sigmoid, and again it will change something, and if you change a ReLU, and it will be different. Now these are all tasks of yours, like what is happening when you change a activation function, what is happening into the unit signal, unit piece, what is the building block which is constructing the f of xy, that is my target. Here it is, the building block is a simple signal, and in this case building block is a smoothed function, that is the activation function. In this case the building block is a cuboid rectangle. And if you allow the sigmoid, here again it is cuboid will turn it topology, turn its shape into some kind of a smoothed cuboid. I don't call it as a cuboid, some kind of smoothened version of the the pillar that that allows, that is a brick, like you can say. These thousands are more than several thousands jointly arrangement of these building blocks uh, constructs our function approximation. So this is what internally the neural network is doing the things. So now what I ask you to uh, for you feel, my exercise is not just this one for you to feel. Take several functions f's from r to r, and as well as from f of x y from r2 to r, and take several activation functions, like one is with heaviside function, other with sigmoid, other with ReLU. ReLU is something like this one. You feel what is the building block, what is the brick, which is constructing the f of x. Okay, you can take up tan hyperbolic. Okay, now you make a kind of notes, or you make a kind of a literature on our own experience. It is not from anything, on our own experience. Draw all these building blocks for how they are function approximating, how they are participating into the function approximation for in 1D as well as 2D. Okay, so I gave some kind of hints through this one, how they are building block, and extended to the sigmoid, how it is smoothing it up. Now your task is to look at this one, how they are doing these two, what are the building blocks, pieces which are constructing the function approximation. And you feel that it not just to know about the mathematics, it is you to dig into the deep of geometrical intuition, uh, how the neural networks by these several so that you are having a complete control of bits and pieces. Even you may not use them to literally draw them, literally kind of visualize in any practical things, but whenever somebody asks you to do some kind of approximation or find a prediction of some data, then immediately you can understand very clearly, okay, this data nature is this way, so that what kind of activation function may do better, that you can think of it in a realistic sense. So these are the few exercises. If you know the building block of each activation function, how it is approximating, then you have a better judgment to decide how to develop a model in a more concrete way, I could say. Yeah, that's what my exercise for you to do that. Okay, that's I can. Okay, with this, there are a lot of things to talk about, but I don't think that this time for this neural network course may not sufficient to cover all those things. I am trying to extend whatever I know up to the level of I can do for you. Maybe. Um, if if we meet some other time, some other place, there are a lot of other things to talk beyond this one. But at least you should know, you should know the the internal structure of neural network, and how it is behaving, how it is how it is. I think by this time you understand neural networks from the theoretical point of view, and geometrical point of view, and approximation point of view, as well as training point of view, as well as the what is called the numerical method, the matrix methods, the point of view. There are several views I have gave you. Maybe I will write them up. One is core analysis theory, uh, analysis, that is how they are functioning, and the matrix language, and uh, training, training from data, and geometric view of neural networks. So these are all views, all the doing the same thing. The analysis talks about, the very first we have discussed all those, why how the neural networks are mathematically defined, and how they are dense and all. That is being translated into the language of matrix and calculus, to look at, make use of those theories into the machine, because theory you can't develop in the machine. We have to apply some kind of numerical methods. Those will be possible only through the language of matrices and calculus derivatives, and the training point of view and the geometric point of view. These are the four ways of looking at the same thing, the neural network. Okay. Um, Now from this, from the next, maybe from tomorrow, I will start something new. That will be completely different topic within the neural network, but not about the architecture, not about the what we started right now. So from that, we'll see uh, where we stand upon that. Okay, if you have any questions, you can freely ask me on this topic as of now.
Sir,
Yeah.
last you have given one assignment, sir. Like we have to make a complete NN class, sir, for back propagation, how error distributed, sir. Then we have to write a Python program for this one, sir.
Python programs I don't want, but Python programs forever sake. I'm not asking for Python programs in any. I am just leaving all the exercises. Do Python. That is for own your own purpose only, for your own experience. So even I say many times that is actually gives a feel how actually the mathematics is run by the computer. But that is your own choice of time and your efforts. But for my thing, you develop in the mathematics and
Okay, sir. Okay, sir.
mathematical way of this one. I think I have given some. I don't remember actually what exercise that is.
Sir, you have given two, three exercises like a problem on problem to this one, sir,
Okay.
and
Yeah.
derive the all the derivation for weights and bias using
Yeah. Yeah.
gradient descent, and after that, how we can separate two class labels in 1D and 2D. After that, how we can create OR gate, AND gate, XOR gate.
Okay.
After that, you will give the how error distributed, sir, back propagation.
Mm-hmm. Yeah. Yes. 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 I remember. Yeah. Yeah.
Yes, sir.
Right. So yeah, these are all theoretical, like theoretical in the sense like these are all like practical, but on the pen and paper only. But this should be suggest you to implement on the computer for our own better understanding, not for me as well as everything is for you only. What level you wanted to dig, it's up to you. Mm, yeah, this XR is one thing. Like, yeah, these are a lot of I'm saying like exercises. These are not just exercises. They give you kind of a feel like yesterday also I gave you these two exercises.
Yes, sir. Yes,
Um,
sir.
yeah, these things you should really feel it, and so you can think of how machine is actually built on the mathematical rules that you can come up with. You don't think of just like these are all the formulas. And if you stay with that, like it is a formula, it is doing, then you don't feel the subject right away. So that is my intention. Like even you try different architectures, different. You take your own whatever visual comes to your in your brain when you are doing it, and take your own choice. Let's say, suppose you take a letter from your name. Uh, let's say if I say NIT, if I chase, uh, if I take an N from the NIT, and if I draw some points like this around this one, and this one are the green points, and there are pink points on this line, and again there are green points on this bottom. Okay, maybe I will keep the pink points inside. Much complexity I'm adding. So how a neural network separates this pink and green? So this is a complex version of. If we keep the pink points this side, and that is quite easy. But if I keep pink points this side, then it would be quite difficult to decide at this juncture. So what kind of then now I did not think, I did not explain, I did not tell you many things like you should explore on your own from with this base structure. What actually allowing you to do multiple layers that you can maybe by this time you achieve it from the exercise XOR. XOR you never achieve with a single hidden layer. You should go for multiple layers. That is why the separation where I read, yeah, this one. This separation of multiple regions here, this one, and this one. These two are same, and this one is different. This is not possible with a single hidden layer. You have to go for multiple hidden layers. Why that is? that you should understand. That is what exercise is not just to explore XOR and write up a program or write up a neural network. It is about why you can't develop XOR with a single hidden layer. Why it is forcing you to definitely go to the multiple hidden layers, at least two hidden layers. It is required that you should feel that is the purpose of this exercise. Okay, the same like why these neural some architectures are allowing not allowing to do it within the single hidden layer. And suppose if you take another architecture like my favorite example, this one I did not tell you, I guess. Suppose if you have this one with these are all green points. These are all green points, and now my pink points are like this. It is actually interesting example to code it up, actually not to see actually in the mathematics. Coding will give you a nice feeling actually. So now the neural network to separate these 2 points. Now again, if I so I am expecting this is the line. I am expecting neural network should produce a line like this, so that they are separating these the green and pink. So what neural network is sufficient to do this? How many minimum neurons are required? These are all questions you should ask yourself. How many neurons are required to separate these 2 points in a 2D? This is a simple line only, line separation, but the data is sitting in a different structure. It's not just like a group of points. Like there are some points in this arc and some points in this arc. How these points and these points are, how they can coordinate to produce the line equation. This is not just to train up a program, it is to think beyond the programming, that how they are coordinating, how these points are coordinating to bring this line equation like this. So what is having the what is the role of these points, and what is the role of these points, what is the role of these points, what is the role of these points are involved to construct this line. That is so important. Okay, this is too deep into the mathematics. And now if I complexity, if I add up something like, if I join these pinks into something like this, not the line. Now you can't do it with the line separation. You know there is no more line now. So now you have to go something like the arc should be separated out. Right? Now again, there is a complexity again here to what neural network, and now the behavior of these points, how they are coordinating to construct this line, this curve. I don't say it is line now. Curve. So these you should explore on your own all these things. So I can provide all my intuitions to work for your own, you know, uh, tasks. These are all personal interests. So these are all comes, most of the things comes out of my own thoughts only. So that's what I'm just, there are a lot of several other things, but there are little complex things, but these can be you can try it up and feel them. So you finally, ultimately, you will be exercises are driving points which allow you to, the subject is becoming much robust by applying several conditions. So applied thinking is the one which you can able to understand the models much better. in mathematically and visually. Okay, that's it for today. I've taken few more minutes extra, but okay. So anything? Uh, so the exercises which I am asking most of the time, you do them, not just for course purpose, just for machine learning, to understand the neural networks and machine learning much better.
Okay, okay, sir. I will try, sir.
Yeah.
Okay.
Okay,
Thank you,
then
sir.
we will meet you tomorrow. Thank you.
Okay, sir. Thank you, sir. Bye, bye, sir.